Well, hello science enthusiasts. Since my last video I received a couple of requests. Matt Botwright asked if I could talk a little bit about interstellar travel, and Divyesh Srivastava asked if I could address a mysterious radio signal that was picked up a few months ago by the Parkes Radio Telescope in Australia. Well, I had originally planned to cover exoplanets in this episode, and I think these topics tie in perfectly. So join me today as we explore a galaxy full of exoplanets and the technology we'll need if we ever want to visit one of those alien worlds. Exoplanets are simply planets that orbit stars other than our own. Ancient writings tell us that philosophers from as far back as 2,300 years ago even pondered their existence. Epicurus, one of the most significant philosophers of the Hellenistic period, even wrote, "There are infinite worlds, both like and unlike this world of ours." Now, although people have hypothesized the existence of exoplanets for thousands of years, proving their existence turned out to be a little bit harder than expected. That was until October 6, 1995, when Swiss astrophysicist Michel Mayor and Swiss astronomer Didier Queloz announced their discovery of a gas giant orbiting a star 50 light years away called 51 Pegasi. The planet they discovered would be named 51 Pegasi b, and then later named Dimidium, a Latin term that means half, referring to the planet's mass, which is half that of Jupiter. Astronomers have gone on to discover 4,389 additional exoplanets, and they keep finding more and more every month. In fact, in the time it took me to produce this video, astronomers have discovered 25 additional exoplanets. So when you compare this rate of discovery to the broader timeline, this has been an explosion of discovery. So let's next take a look at how astronomers have been making these discoveries. Exoplanets are nearly impossible to detect using telescopes because the stars that they orbit outshine everything near them. The first method that allowed astronomers to detect exoplanets is called the radial velocity method. Here's how it works. Most of us learned in school that the planets orbit the sun. Well, that's not 100% accurate. The sun and the planets actually orbit a location within the solar system called the barycenter. If you were to build a scale model of the solar system on a flat disk, the barycenter would be the point where you could balance that disk on your fingertip. And that balance point moves around a bit as the planets orbit the sun independent of each other. Since the sun accounts for around 99.8% of the total mass of our solar system, the barycenter is actually pretty close to the center of the sun. This illustration shows you the location of the barycenter over a 51-year period. You can see that in 2022, the barycenter will be located around 1 million miles from the sun's center. As the sun orbits this barycenter, if you were outside the solar system looking at the sun, it would appear to wobble. And it's the wobble that reveals the presence of planets. Astronomers can't yet detect the side-to-side or up and down motion of stars because they don't have instruments that can measure those motions very accurately. However, thanks to something called the Doppler effect, astronomers are able to measure the star's back and forth motion with amazing accuracy. The Doppler effect is the change in frequency of a wave in relation to an observer. An audio example of this effect may be if you ever listen to an ambulance passing you by. If you were ever in that situation, you would have noticed that when the ambulance is approaching you, the pitch of the siren is higher than when it's moving away from you. Similarly, when a star moves toward us, the light waves are compressed and the frequency of the light changes, shifting the the color of the light toward the blue end of the color spectrum. And when the star is moving away from us, color changes a little bit more toward the red. It shifts toward the red. So we call these shifts either red shift or the blue shift, and it tells us whether the star is moving toward us or away from us. And the amount of this shift can be measured very accurately, and they can tell how fast that star is moving toward us or away from us. The more massive a planet and the closer it is to the star, the greater impact it has on the star's motion, making it easier for astronomers to measure. And this explains why most of the exoplanets that have been discovered with this method happen to be bigger gas giant type planets orbiting their star very closely. While the radial velocity method measures changes in the color of starlight, another method developed in the early 2000s called the transit method measures the periodic dips in intensity of light emanating from a star. The bigger the dip, the larger the planet is relative to the star. In 2009, NASA launched a space telescope designed to detect exoplanets using this exact method. And during the telescope's lifetime, meaning before it ran out of fuel in October 2018, it had detected over 60% of the exoplanets we know today. One downside of the transit method is that you can only detect a planet if it's passing directly in front of the star. So for instance, if the planet is orbiting in a perpendicular motion from our perspective, it would be undetectable. In 2006, scientists developed an exciting new exoplanet detection technique that capitalizes on the effect of gravity. Gravitational microlensing is an effect produced when one star passes in front of another star and the star in front bends the light coming from the more distant star. The light from the background star gets amplified by this lensing effect, and if there's a planet in orbit around the star in front, then an extra bump will appear when that would otherwise be a smooth light emission curve. The exciting thing about gravitational microlensing is that it's extremely sensitive. They're able to detect smaller rocky Earth-side exoplanets using this method. The disadvantage is that you can't plan for these events to occur. You basically have to get lucky and catch them when they happen. Now, there's no way to know how many more exoplanets astronomers will discover from this point on, but astrophysicists have extrapolated from the current discoveries that there are at least as many planets in our galaxy as there are stars, which means there are more than 100 billion exoplanets in our galaxy alone. And out of that number, NASA estimates that around 300 million may be habitable. So the next logical question is, how many of those habitable planets contain life? Well, the James Webb Space Telescope, scheduled to launch later this year on October 31st, may give us some clues, and color will be the key. As a planet passes in front of a star, light reflected off of the atmosphere of an exoplanet will be split into rainbow color spectrums that the James Webb Telescope will be able to translate into gas types. TRAPPIST-1, an ultra-cool dwarf star slightly larger than Jupiter, will be the primary target for the James Webb. Located only 39 light-years from Earth, this star contains 7 Earth-size worlds, of which 3 are located in the star's habitable zone. Teams of astronomers will analyze the atmospheres of these 3 planets to see if any of them are similar to Earth. For the sake of argument, let's imagine that we discover one of these planets has an atmosphere like our own. This would give us a clue that the planet may contain life, but it won't be proof. The next required step will be passed on to space telescopes of the future, which will eventually be able to discern biosignature gases like ammonia, nitrous oxide, or hydrogen sulfide in the atmospheres. You may have heard recently about one of these biosignature gases being discovered in Venus's atmosphere. The gas that was discovered is a stinky gas called phosphine. Some scientists believe that it could be possible that microorganisms are living in the atmosphere high above Venus's surface. And as we perfect these atmosphere gas detection and cataloging techniques, perhaps one day we'll be able to determine if we've discovered intelligent life. Intelligent life might leave behind signature gases like we leave here on Earth, pollution as an example. I want to believe that there's intelligent life out there somewhere, and I really believe the probability is high. But I question how close to us intelligent life is. Of the 100 million potentially habitable worlds out there, let's say 1,000 of those worlds contain life, and out of that 1,000, 2 contain intelligent life. Our world and one other. Galactic distances are mind-blowing. Let's say that a civilization on the far side of the galaxy found a way to send a radio signal to us. It would take more than 50,000 years to reach us. We don't even know if we'll be here in 50,000 years. Or what if they sent the signal millions of years ago and it arrived here millions of years ago when we weren't even evolved yet? Or maybe they haven't evolved yet and they'll send the signal millions of years from now. Think about how short a period of time that we've been here as a technological society on the Earth. The first radio transmission happened in the year 1900. Now, that signal has only reached about 512 stars so far. If you look at the galaxy and where we are, that's only about this far. And while it's interesting to ponder how far radio signals travel over time, also remember that they weaken by something called the inverse square law. This means that the signal weakens exponentially to the distance that it travels away from the Earth. So all of our terrestrial radio signals become indistinguishable from background noise just a few light years from Earth. That said, in 1974, the Arecibo telescope in Puerto Rico sent the most powerful, deliberate broadcast ever with the intention of contacting an alien civilization somewhere. The message contained information about basic chemicals of life, the structure of DNA, Earth's place in the solar system, and even a digitized stick figure of a human. The transmission was equivalent to 20 trillion watts, which would be distinguishable across the galaxy. But in order to get the signal to travel so far, they had to point it at a very tiny patch of sky. So today the signal's heading toward the M13 globular cluster that's like 23,000 light years from Earth. And so far the signal has traveled 47 light years. Bottom line, aliens probably don't even know we're here. While no alien civilization is likely to have picked up on our television or radio broadcast signals yet, we might accidentally eavesdrop on somebody else's signal. Back in December 2020, there was a report of a mysterious radio signal coming from the general direction of our closest neighbor, Proxima Centauri. Proxima Centauri is only about 4 light years away from Earth, and it hosts 2 exoplanets. One of those exoplanets is slightly more massive than Earth and sits in the habitable zone of the star. The Breakthrough Listen project detected the signal using the Parkes radio telescope in Australia. The signal had a frequency of 982.002 megahertz, and it lasted for 30 hours and then it stopped. It was dubbed BLC-1, which stands for Breakthrough Listen Candidate 1. When the story leaked out, it had many people excited. I have to admit that I was excited too, although I was cautiously excited. I had heard rumors in the past of mysterious radio signals that turned out to be, like a microwave in the kitchen of a telescope observatory and things like that. This latest signal piqued attentions worldwide because it had all the properties of a radio transmission originating from a technological source. The Breakthrough Listen team hasn't released an official report on this signal yet, but they did release a statement in February of this year indicating that they're 99% sure the origin of the signal probably lies with human technology rather than alien technology. But they haven't concluded their studies, so we'll have to wait for them to finish their investigation. Now, while as of today there have been no confirmed radio signals that were transmitted from an exoplanet, some people believe that intelligent life may have visited our planet already and may even be here with us now. In April of last year, the Department of Defense authorized the release of 3 videos of unidentified aerial phenomena. They released the official videos in an attempt to clear up misconceptions by the public on whether the previously leaked footage was real or not, and said that the phenomena remains characterized as unidentified. If and when we do meet the aliens, I recommend that we gain as much knowledge as we can about their spacecraft propulsion technology, because as advanced as you may think our technology is, it's far short of giving us the capability of sending manned spacecraft to even our closest neighbor, Proxima Centauri. The fastest spacecraft departing our solar system at this time is Voyager 1. It was launched in 1977, and after completing its primary mission, which was to survey Jupiter and Saturn, NASA pointed it straight out of our solar system, and today it's traveling at 38,000 miles per hour, and it's around 14 billion miles from Earth. And while 14 billion miles may seem like a long distance, it's not even close to the 25 trillion miles distance needed to travel to Proxima Centauri b. To bring this distance into a scale that we can visualize, if Proxima Centauri b was a football field away from the Sun, Voyager 1 would be at the 2-inch yard line on the field, and at its current speed it will take another 75,000 years to reach the distance equivalent to Proxima Centauri. So that's the fastest object departing our solar system. How about the fastest object we've ever put in space? That would be NASA's Parker Solar Probe, the first ever mission to travel directly through the Sun's atmosphere. The probe is currently traveling at 330,000 miles per hour and will reach a maximum speed of 430,000 miles per hour in 2024, roughly 10 times the speed of Voyager 1. Even at this mind-blowing speed, it will take 6,636 years to reach Proxima Centauri b. So do you see my point now about asking the aliens for some help with their propulsion technology? I'm joking, but you can see why our current speed records are just not going to make it. No country or group of countries is going to invest in a manned scientific mission to an exoplanet that will take 300 generations to reach. We're going to need a technology that enables us to reach our nearest neighbor in a realistic time frame, like 40 years max, if we want to see the investment in a mission like this. And that means our spacecraft are going to need to reach speeds of around 10% the speed of light, or about 70 million miles per hour. It turns out that accelerating to this speed using conventional rockets is impossible. We can actually calculate the amount of fuel needed using Tsiolkovsky's rocket equation. Let's say we want to send a toothpick for our payload, and let's be conservative and give our journey 100 years, because I want to hammer this point home. To send a toothpick and make it there in 100 years, the amount of fuel you'll need is equivalent to the mass of the known universe multiplied by 10 to the 2200th power. That's a 1 with 2200 zeros after it. Scientists have dubbed this problem as the tyranny of the rocket equation because it's impossible to overcome with conventional rocket fuel. The fuel requirements grow exponentially the faster you want to go. You end up sending fuel to propel fuel to propel fuel to propel fuel to propel your rocket. So let's take a look at a couple of other more efficient technologies that are within our reach. Ion thrusters is one of those technologies. They work by shooting electrons through a stable gas like xenon, creating a cloud of positive ions. Electromagnets then enhance the ionization process, and when the ions pass through the exhaust, they're expelled at 90,000 miles per hour. Ion thrusters are a lot more efficient than rocket engines, but it comes with a trade-off. They don't produce a lot of thrust. Our best ion thrusters only create a half a newton of thrust. That's equivalent to the force that I'm exerting on this candy bar to keep it from falling to the ground. Not a lot of force. This technology was actually tested by NASA on their Dawn spacecraft in 2007, so we know what the practical performance of these thrusters are now. Dawn carried 937 pounds of xenon fuel to complete its mission. An acceleration test was performed at full throttle, and the thrusters were able to change the velocity of the spacecraft by a net 60 miles per hour over a 4-day period, expending 37 ounces of xenon. You can extrapolate how much xenon fuel you need to get a small unmanned spacecraft like Dawn up to relativistic speeds, like 10% the speed of light. And again, we meet the tyranny of the rocket equation. So we've pretty much resolved that we're not going to get to Proxima Centauri b using conventional rockets or even ion thrusters. However, another technology called solar sails have actually shown some promise. The benefit of a solar sail is that you don't need to carry the fuel along with you because they're propelled by light. That could be light from our sun or light from another source like a laser. Japan tested a version of a solar sail in 2010. They launched a 700-pound spacecraft called Icarus, equipped with a 2,100 square foot reflective sail that included 64 thin film solar panels and 80 variable reflective liquid crystals for power and some steering. And the experiment was a resounding success. Icarus was able to accelerate its speed to 900 miles per hour. The only drawback? It took 3 years to reach that speed. The force that the sunlight exerted on this 2,100 square foot sail was about the same amount of force that my finger is exerting on this coin. Not much, right? It's also important to note that this small amount of force drops the further away the sail is from the sun. and it drops quickly by the inverse square of the distance between the sail and the sun, which means acceleration diminishes very quickly the farther away the spacecraft is from the sun. So at distances beyond Mars, the sun becomes too faint to even push the solar sail at all. It might be possible to get the sail speed up quickly before it's out of effective range using strong lasers. Laser-driven light sails are the basis of a project announced in 2016 by venture capitalist Yuri Milner and the late Stephen Hawking. The project named Breakthrough Starshot envisions a swarm of around 1,000 stamp-sized spacecraft, each weighing about a gram, attached to a light sail measuring 13 feet across. Each craft would be equipped with navigation, communication, and power storage, but the goal is to keep the total weight of each craft to no more than a few grams. The small mass would allow for quicker acceleration. If the laser assist could increase the speed of each sail to 20% of the speed of light, the swarm of spacecraft could make the trip from Earth to Proxima Centauri in about 22 years. The reason for sending 1,000 of these spacecraft is to increase the possibility that one of them might succeed in making the journey. If successful, the hope is that one or more craft can snap a few images of Proxima Centauri b and send them back to Earth. The resolution of the images would be high enough to resolve the planet's features. So far, scientists and engineers leading each aspect of this program see their biggest challenge as building strong and accurate enough lasers to accelerate the light sails to 20% the speed of light. But they say that Moore's law should improve technologies in time to achieve a launch of a prototype by 2036 and a full mission launch by 2048. So keep an ear out for updates to Project Breakthrough Starshot, as this could be our first attempt to reach the stars. As for sending people to the stars, we're further away. We already know that chemical rockets are not going to work. Chemical fuels produce thrust through chemical reactions that rearrange electrons. But electrons are only a fraction of the potential energy in an atom. More than 99% of the atom's energy is in the nucleus. So a kilogram of fuel that is chemically reacted produces thrust from only 1 milligram of its total mass. Another way to say this is, even at its most efficient use, 0.0001% of the mass of the fuel is converted into energy. If we could find a way to master nuclear fission reactions for our spacecraft's thrust, that efficiency value could change significantly. Instead of relying on just the atom's electrons to produce energy, the fission process capitalizes on the nucleus of the atom, allowing for up to 0.1% of the fuel mass to be converted into energy. If we went one technology further and focused on nuclear fusion reaction, we'd gain even more efficiency. Nuclear fusion is the same process that occurs inside the sun. If we could find a way to use this technology to propel our spacecraft, about 1% of the total fuel mass could be converted into energy. Fission and fusion propulsion systems could effectively reduce our travel time to Proxima Centauri b from several thousands of years to centuries or even decades. And if we want to go all out in terms of efficiency, we could pursue matter-antimatter annihilation. Although just theoretical at this point, a matter-antimatter annihilation engine would convert 100% of the mass of both the matter and the antimatter into pure energy. This is the ultimate in fuel efficiency. The difficulty will come in the creation of a stable antimatter that engineers are able to isolate from normal matter when it's not in use, and the energy needed to produce it in large enough quantities that make it practical for interstellar travel. But if scientists and engineers can work through these problems with just 38,000 tons of matter-antimatter fuel and a rocket engine that's 100% efficient, you could accelerate a 1,000-ton payload to 1G continuously for half of a trip to Proxima Centauri, and then decelerate at 1G for the last half of the trip. You would arrive at Proxima Centauri 5.93 years after you departed Earth. It could be our fastest way of interstellar travel. So to recap, for thousands of years, humans pondered the existence of worlds outside of our solar system, and then within the last 30 years, astronomers discovered over 4,300 exoplanets. And NASA estimates that there are at least 100 billion exoplanets just within the Milky Way alone, of which 300 million might be able to sustain life as we know it. At some point, astronomers are bound to discover a planet that can sustain life, or a planet with life, or maybe even a planet with intelligent life. And then we'll be at a critical decision point. Do we visit the planet, or do we not? We're a species of explorers, so I can tell you, we're going to go. But current propulsion technology can only get us to our closest neighbor, exoplanet, in 6,000 years. And that's too long. We might be able to send tiny nanocraft to our closest neighbor using solar cell technology and super strong lasers, but that's about the extent of our closest technology. To become interstellar explorers, we're going to need a propulsion system that hasn't been invented yet. A technology that feels out of reach. But every time I get a feeling that a space technology is out of reach, I remember how far we've come already. I think about the speech that President John F. Kennedy gave in 1962, announcing to the world the plan to go to the moon.
But if I were to say, my fellow citizens, that we shall send to the moon 240,000 miles away from the control station in Houston, a giant rocket more than 300 feet tall, made of new metal alloys, some of which have not yet been invented, capable of standing heat and stresses several times more than have ever been experienced, fitted together with a precision better than the finest watch, carrying all the equipment needed for propulsion, guidance, control, communications, food, and survival, on an untried mission to an unknown celestial body, and then return it safely to Earth, re-entering the atmosphere at speeds of over 25,000 miles per hour, causing heat about half that on the temperature of the sun, almost as hot as it is here today, and do all this, and do it right. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills, because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win.
And 10 years later, we were on the moon. So I remain hopeful that our spirit of exploration will take us beyond our solar system. All we need is a well-defined vision and a will to follow through. Okay, that's all I have today. I hope you enjoyed this episode. If there are areas of the universe you would like me to explore, let me know in the comments below. Please share this episode with friends and family if you think they may like it. Click the subscribe button and also the little alarm bell if you would like to be notified of my next episode. And stay safe out there, friends.